Okay, so now we're going on to we're done with chapter 2, and we're moving on to chapter 3, which are diode circuits. So it's going to introduce diodes, and now we want to see what we can do with them. Although they're also, starting point for the transistors, but the diodes themselves have some circuits that are good for like doing a diode. So let's see. Okay, so here's what we're going to cover initially. So first we're going to talk about the different models of a diode. So we're going to talk about an ideal model diode. We talked about how the diode equation, if you draw the voltage across a diode. So if this is V and this is I, if we draw that, a real diode will give us something like this. This being I sub S, and this being something like I is equal to I sub S exponential of V over Vt minus 1. Something like that. So we said that's the actual equation for a diode, but we can represent that as, to simplify it, whoops, that's too close to the other one. Let's pick a different color, green, okay. We can do something like this, just say it's a simplified model, something that goes on at a certain point. But then we'll notice, we'll also talk about another one which is even simpler, which is something that just goes on at V equal to 0. So these basically make circuit analysis easier. And, actually it was an interesting email that one of you guys sent me, William sent me, is about whether he could use MATLAB to solve these iterative problems. And, I think, like, whether you use MATLAB or SPICE, etc., these are good tools for analyzing, especially SPICE, I think, is going to end up being a good tool for analyzing a circuit you already have. But you need this we need to have some simplified models for building circuits by hand and doing quick analysis when you do the actual design. Because you have to have a feel for how the circuit's working. Okay. Let's see. And then after all this, we're going to talk about the different applications for a diode. So one of the major ones are regulators. Regulators are things that they translate a voltage to another voltage. A good example is, and then we'll talk about rectifiers and limiting circuits, but let's talk about voltage regulators. So this is one of the probably most important applications of a diode. So let's say you have you're trying to plug in your your cell phone. So you got your cell phone and you want to charge it up. So this guy, the cell phone has chips in it, and it needs, say, a DC voltage of 3.5 volts to charge it up through your USB-C or whatever you got, micro USB. But the problem is, when you plug it into the, let's see, you're gonna plug it into the wall supply. Okay, so this is the wall plug. And as you guys all know, the plug has 110 volt AC. So this is what's a DC of 3.5. The wall has a AC voltage of 110 volts. So you need to build something in between. This is your charger that you get from Apple or Samsung or whatever your phone is from, that basically translates that alternating current signal into a DC voltage for your phone or your laptop or whatever to charge up. Okay, so this is another drawing of this thing here, which is that, you know, the main, at least in the US, the plug's output is this 60 hertz sine wave, and at 110 volt RMS output. The peak is 110 volt times square root of 2. I always forget what that is. I think it's around 150 volts or something. But the key is this guy has no DC component, okay? Because it has an equal number of signal values on top of positive voltage values as negative voltage values. Basically, by definition, has no DC component. So you need to find a way to take this from an AC signal to a DC signal, okay? And then basically you end up with needing a circuit like this, which is, you know, the first step is to drop down the voltage, because 110 volts is problematic to begin with, okay? So what you do is you have a basically like an inductive coupler by, I don't know if you guys are familiar with this, but you don't need to be for this discussion. Basically what it does is it takes a, depending on an inductance value of this side of the coupler and this side, you can drop down the voltage just by buying this component. Okay, so let's say we use that to come up with something with a lower amplitude, which is, you know, in this example is 4 times square root of 2, which is, you know, probably around 5-6 volts or something like that. So that we can do with transformer, with a transformer or inductive coupler. But then the problem is still, so now we got the right voltage, but the problem is how do we create a DC voltage out of that? And so we need something basically to take this voltage here, which is redrawn here, which has equal positive and negative voltages. This guy, because it has equal positive and negative voltages, again, doesn't have a DC component. What you know, a good way to would be, a good thing to do would be to take this signal and just pass the positive areas. Okay, so that's one way to basically, so now this signal here, this guy here has a DC component because we got rid of the negative value. So if you integrate this voltage over time, you'll actually end up with a DC component. And so, and one of the main things that we use a diode for is a way to get from this, basically to get rid of half of this kind of signal to get ourselves a DC component. And then we can do various things to that, in addition to that, to then come up with this 3.5 volt DC value. Do you guys see how, like, the wall does not have a DC component? Anybody have questions about that? Basically, if you integrate something like this that has equal positive and negative, exactly equal positive and negative values over time, if you integrate that over time, you're going to get 0, because the positives are all you know, canceling out the negatives. So basically, you know, you won't have any DC value. So you have to find a way to get a DC value, and one of the easy ways to do, or if you have a diode, it's an easy thing to do, is to get rid of the negative parts, for example. You could have gotten rid of the positive parts, but then you'd end up with a minus 3.5 or something like that. Okay, so so let's say if we had something like a diode actually is something that can do this. So for example, let's say you had your input x of t was your voltage? Let me draw this. Yeah. So let's say this was ground for the sake of discussion. Okay. Now remember what happens in our in the mode of an ideal diode. Okay, so we said now by an ideal diode, I'm going to say one that just turns on. So if this is V, this is I, it turns on at V equal to 0. And at V equal to, when the voltage is negative, it doesn't conduct at all. So it's like an open circuit. And when V is positive, it's like a short. So when V is negative, so out here, it looks like an open circuit. Okay, when it's this, when V is positive, it's a short circuit. I think so. So I think I actually drew this wrong. Let me do this. Draw this like this. No, I think I had it right. Sorry, guys. That's negative. Yeah. I wanted to draw it like this. Okay, so what happens here? So when x of t is on a positive cycle, when it's like this, okay? No, you know, I think this is, let me just do it so that it's exactly like what they're talking about. Okay. Okay, x of t, and then this diode, and this is some small resistor value. Okay, so what happens is when x of t is positive here, okay, so this guy, let's say it's close to ground value. So when this guy's positive, this guy here looks like you're just dropping a voltage across a resistor. Okay, so the output y of t just looks like the voltage is, there's no resistance. Since there's no resistance here, this voltage x of t just shows up at y of t. It's exactly the same over here. Okay, so the diode is acting as a short. As soon as the x of t goes negative, so out here, as x of t goes negative, this diode, as soon as it goes negative out here, the diode acts like an open circuit. So what happens is you get the x of t, and then it's an open, and then we have a resistor to ground. So now so basically y of t just goes to ground. Okay, so basically this goes to ground when x of t is negative, and it follows, y of t follows x of t when x of t is positive or above ground. Does everybody follow that?
So, Professor, it opens and closes really fast, right? Like it opens and closes, that's a cycle. Like that's exactly how fuel injectors work, right? I mean, but those are solenoids, but that's exactly how it works, right? Like it opens and closes.
It opens and closes. I mean, there is a delay between it opening and closing, and you know it changes resistance, etc. But in the sense of thinking of it in terms of an ideal model, it just opens and closes immediately. There's no delay or anything. Is that what you meant?
Yeah. Okay.
Yeah.
Thank you.
Sure. So actually, you know, the way it tries to give you guys a visual, the book tries to give you a visual, is like a water valve. like something that has a hinge, whoops. So it has like a one-way stopper with a one-way hinge. So when water goes like this way through this hose, the hinge opens up and lets water through. Okay, but if the water goes this way, oops, oh, sorry guys, I'm moving stuff around in a bad way. Yeah. Wow. Okay, here we go. If water goes this way, the hinge opens up and lets the water go through. If the water goes this way, the hinge, the way it's set up, is it's blocked, so the water does not go through. Okay, so that's sort of this ideal model of an ideal diode like that. So again, if you looked at this, okay, as what we said, if it was a real device, a real diode, it would do something like this. But to make life simpler for us for circuit analysis, we're basically pretending like it does this. And this is a good model for a lot of sort of hand calculations just to get a feel for something. So anyway, this is our ideal model. And the idea is when the anode is greater than the cathode, so when the anode is greater than the cathode, or out here, it acts like a short, like a switch that closes. So out here, it's a short. So anywhere out here, it looks like a short, basically. Okay. Do you guys see how this line here is a short out here? It's basically providing like basically infinite current as soon as you turn on. Okay, so it's just jamming the current in there. So if you had a voltage source, no matter, let's say you had a resistor here, no matter how small this resistor is, this guy, this V sub X, would be able to put enough current out that you would just basically, you'd enforce this value here, okay? And then when the anode is smaller than the cathode, when this guy is less than this guy, it's like an open switch and no voltage flows. So it'll just be like, any questions about that? So we're basically introducing this thing called an ideal diode model that's meant to make circuit analysis simpler, just because we have this case where it's sort of this diode just as a switch goes on and off, and we don't have to deal with, you know, exponential characteristics like you have here. You don't have to worry about this small I sub S current that you have here. You just say it's a switch. The switch has zero resistance when it's on, so it's a dead short. And when it's off, it's just off. It's an open circuit. Okay. So let's look at what happens if you put connect diodes in different ways. So let's say this case. Okay, so this is supposed to be an example of what happens with this kind of a simple model. So remember, this part is called the anode. And this is called the cathode. I mean, sorry. So this is this anode, this is the cathode of D1. So actually, let me write it this way. Okay, so sorry. Okay, so this point is the anode of D1. This guy is the cathode of D1, and it's also the anode of D2, this guy, and this is the cathode of D2. Okay, so what happens is if this point goes high, okay, then this point follows this point, because this guy, remember, this guy looks like the D1 will just close, looks like a closed circuit. And that voltage from A will then show up at D2, and D2's anode will also be higher than its cathode. So it'll also turn into a closed switch. So if you hook up two diodes in series like this, sort of back to back, then you'll get like a short across this in the case of A. Okay, so that's gonna, A is gonna conduct from A to C. Okay, now let's look at this example of B. Okay, so for the case of B, again, the anode here of D1 is going to be higher than the cathode of D1. So from here to here, it'll look like a short. But here, notice we hooked up the anode of, sorry, the cathode of D2 to, sorry, we hooked up the cathode of D2 to the cathode of D1, okay? Which means that now this cathode of D2 is gonna be higher than its anode, and then that means that it's gonna act like an open switch. Okay, so in this case, when the diodes are kind of facing each other, you do not get a closed switch from A to C. Okay, does everybody see that?
Yep.
Okay, so it's just a real simplified way of looking at a diode. And then C, you see that we've got, the first thing is we've got the cathode of D1 here. The anode of D1. And since the cathode of, in this case, of D1 is higher than the anode, A is now an open switch. So it doesn't really matter what happens to D2 in this case. D1 is already an open switch, and again, you don't get any, so you don't get anything here, and you don't get anything here. Okay, so also putting stuff in series, you have to make sure, for example, the diodes are facing each other when you put them in series. Okay, and you know, depending on, maybe I just said that wrong. You have to make sure you put the diodes facing the same direction when they're in series to let them conduct, and also then also depends on what A is compared to C. But in the case of a perfect an ideal diode, I'm sorry, in the case of an ideal diode, this circuit, only in the case of an ideal diode, this circuit is equal to this circuit. And these two other ones, these are, they just look like opens. Okay. Okay. Then when you, boy, this thing got mangled again. Sorry, guys. Okay, so let's say, okay, so basically this is what is the ideal characteristics of a ideal diode. Okay, so when okay, so in this case, this is what you get. When the voltage is, so if you, let's say you had a short, okay? The case of a short, what happens is as the voltage basically can't move higher or lower, right? It'll just, the resistance is 0, the current is basically infinite. As soon as the thing turns on, the current becomes infinite, okay? And then in the case of an open, no matter what, so if R is infinite, like in this kind of case, no matter what the voltage does, okay, because R is infinite, it just looks like a flat line. Okay, and then an ideal diode, basically, if if it's cathode, okay, so if the cathode is, sorry, let me just put it another way. If the anode is higher than the cathode, so you're out here, it looks like a short, that diode. Okay, it looks like a switch. If the anode is lower than the cathode, then it looks like an open circuit. So it looks like this guy. Okay, does that make sense to everybody?
Yes.
Yes.
Okay, great. So let's look at an example here of what happens if, let's say we, instead of putting stuff in series, we put them in parallel. Okay, so let's say we had a voltage, and then you put a diode facing down and a diode facing up. Okay, can you guys think about drawing the E sub x over I sub x curve? Try taking a shot at that and see what it looks like. Okay, and again, notice these things are pointing opposite of each other, but they're in parallel.
Would it be like a square wave or something?
Like out here. Well, okay. Let me just. That's a. Was that William?
Yeah.
Okay. So think of it as square wave. At least the square waves I'm familiar with. The square waves I'm familiar with is they have time as one axis, and you'll see a change in voltage or change in current. So this is voltage or current. Did you mean something like this?
Yeah, I see why that wouldn't work because it's not based off of time. It's just current and voltage.
Yeah, but it's a really good point. So we haven't, I mean, at some point down the line, we're going to talk about time. But at the moment, we're just talking about voltage versus current. So sort of, we're not talking about anything transient at the moment. So let's think about what happens here. Okay, so let's say we're out here. Okay, so let's think about this. So let's say V sub x is positive. Okay, so this point is positive, more positive than this point. Okay, if this point is more positive than this point, let me just call this D1. What happened to D2? Is D1 on or off if this is positive, more positive than this point?
D1 is on. It becomes a short.
Yep, exactly. So at this point, D1 is on. So around here, okay, what it looks like is Vx, and D1 is a short. Then here in this area, when VR is positive, is D2 on or off?
It's an open.
It's an open. Yeah.
It's off.
It's off or it's open, whichever way you want to look at it. Okay. So that's what that looks like. Looks like we've got a short across the voltage source. Okay. And then here, when Vx is negative, is D1 on or off? When Vx is this point is more negative than this point, D1 is on, okay? Sorry, is off. D1 turns off here because this point is more negative than this point. But D2 turns on, becomes a shorted switch. Okay, so when you do this, you end up getting a situation where regardless of which polarity Vx has, okay, whether you're here in the positive side or negative side, you always have a short across Vx to ground. So basically you always end up getting a short in the current. Okay, so it kind of looks like this. So you basically, regardless of which direction it is, the X is pointing to, you just always get a short. Okay, and this is called anti-parallel connection for an ideal diode. Now you might ask, well, why are we even talking about this? It just looks like a short, but it'll come up later that if you were not using an ideal diode model, you would actually get, you know, at some point you would get one to turn on and while the other one, sorry, at some point they could both be off. And so it becomes kind of an interesting circuit. But in the case of an ideal diodes, if you hook them up like this, so anti-parallel means parallel would mean that they're both pointing in the same direction. Anti-parallel means they're pointing in opposite directions. You just get a short across them. Okay. All right, let's see. Okay, let's see. Okay, let's use another example. Let's say we have a voltage source V sub X. It's getting a little trickier here. Okay, so let's say you had this. Don't you guys think a little bit about what would V sub X versus I sub X look like? Again, it's not a function. We're not talking about a time domain here. So just imagine a V sub X, just we slowly tweak it up to go high and slowly tweak it up to go low. Okay, so let's look at this. So when V sub X, let's start at the negative. Let's say V sub X is, this is like something you guys will see over and over again when we analyze these kind of circuits. First we say, okay, let's say V sub X is very negative. So it's like out here somewhere. Like it's V sub X is very negative. What does this look like? If V sub X is very negative, this point, let's say this point is at minus 100 volt. Okay, and this point is at 0. So V sub X is very negative. It's like out here at minus 100 volts. Okay, this diode, D1, this side, whoops, this side ends up being lower than this side, okay? Meaning that it's a, if this side is lower than this side, okay, it'll look like a, it just looks like it's open, right? So it'll look like this. Sorry. For very negative v sub x. Okay, and notice we're drawing I sub x versus v sub x. Okay, so in this case, what is I sub x? So if I was just going to plot v sub x out here, what would I sub x look like? What would the value of I sub x be?
0.
0. Yep. So it'll be on this horizontal axis, and in fact, it'll stay 0 all the way until v sub x becomes 0 and then turns on. Okay. Once v sub x, so for v sub x greater than 0, what happens is this diode turns on, because if the v sub x is greater than 0, this side is going to be bigger, higher than this side. So it means it will turn on the diode. And this is what it'll look like. Oops, I don't want to draw it. So again, remember we were trying to draw I sub x versus v sub x. So here, if I just get rid, so I'm going to redraw this. Okay. Okay, so in this case, what we have is I sub x is basically you're putting a voltage across a resistor, right? So V is equal, I always have to do this. V is equal to IR, so I is V over R. Okay, so it's V sub x over R. That means when V sub x goes positive, we'll get, so this, what does this look like? This looks like a line, right? If you're gonna draw I sub x versus V sub x, it looks like a line with a slope of 1 over R. Okay, so what it'll look like is this. So it looks like a line, and the slope of this line is 1 over R1. So this is kind of an example of how you would look at a sort of an ideal diode, and then we'll talk about. So we'll like go over and over this, because in chapter 3, what we're doing is we're getting used to these different models of diodes. The ideal dot model. Then there's another model called constant voltage model, which is a little, I mean, just a little bit more sophisticated than the ideal model. And then the exponential model. And we're just going to look at like what the differences between these are and how you can analyze circuits. But you can see kind of when it comes to ideal model, we went from, you know, these circuits like the second problem on the quiz 1 that we just had. You guys had to go through like 2 iterations of figuring out voltages and currents and all that stuff with exponential values and I sub s, etc. So when you use that model, it takes a while to kind of figure out what these things are doing. When we're doing such a simplified model, like in this case, it gives us a less accurate result, but let's say that less accurate result's okay. It's just really simple to analyze it. You're just looking if the diodes are on or off as switches, and that's basically where you limit it to. So just a way to simplify circuit analysis when it's called for. Any questions? Okay, guys, so we'll pick up here on Thursday. Thanks.
Thank you, Professor.
Professor. Have a good one.
Thanks, Professor. Thank you, Professor.
Thank you.